There's one more thing I want to tie up this week, which is kind of, it's a slightly, doesn't quite fit in here, but we've got to introduce it at some point. And now now that we've spoken about the phase response and how it sort of emerges out of the pole zero diagram, this is a reasonable time to introduce it. So this is the idea of thinking a little bit more about phase, paying a little bit more attention to the phase of systems, and in particular thinking about how it corresponds to a timing shift. And what we find is there are two different kinds of time shift that are implemented by a filter, called the phase delay and the group delay. So if we have a very simple case, single sinusoid coming in, x of n equals cosine omega 0 n, then we know that if we put that through a system, the output y of n will be h of e to the j omega 0 for that frequency times the original frequency, which in sort of magnitude and phase terms is the magnitude of h of e to the j omega 0 times cosine of omega 0 n plus theta of omega 0, where this is just the phase of the DTFT at that frequency. And so what we're saying is the result of putting the sinusoid through the system is a scaling of the magnitude, a gain, and a shifting of the phase, moving the phase, a phase shift. Now this expression here is kind of the place where the time variation comes in, right? This is our time. We have time scaled by omega 0, then we have the whole thing shifted by some value, which is the phase. But we could sort of factor the phase shift into the time index here, right? So if we have it, say it's omega 0 times some time index, then we could interpret what the filter has done as shifting that time index by a little bit, such that it's the amount of time that corresponds to the actual phase shift that the filter imposes. And there's no real difference between these two. This one looks a little bit more labored in the way that we've written it down. But if we had a single expression for cosine omega, then this would seem more natural, because now it's just cosine omega of n plus this offset. And this offset is basically behaving like a time shift. And so we can call it the phase delay, tau sub p, and it depends on omega 0, right? It's going to be a function of omega 0, and in particular we can see that it's just, if we want to make it a delay, that is, it's something that we expect the system to have some transmission delay, that you can't have stuff coming out before it goes in, but you can have stuff coming out after it came in. So we want to have this as a delay, which means we want to subtract it from n, because that's how delays work. So we want negative tau p of omega 0 to be theta of omega 0 divided by omega 0, or tau p, the phase delay of omega, to be the negative of the phase response at that frequency divided by the frequency. And so all we're doing is expressing the phase response as a proportion of the total phase per sample, the frequency, the normalized frequency of that frequency. And that gives us a result in samples, which we can interpret as the amount of delay that a signal of that frequency experiences. And so it's, again, this is a definition, and it really isn't anything more than algebra. It's just a way of expressing the phase shift in the units of samples, basically. So for our three-point filter, alpha, beta, alpha, here was the full complex form of the Fourier transform, right? This phase term and this magnitude term. So the phase of this thing is just minus omega, and so the phase delay, which is theta of omega divided by omega, is minus omega, so negative of theta of omega divided by omega is negative of negative omega divided by omega, which is just plus 1. And so what this is saying is that this particular filter imposes a phase delay of one sample, regardless of the frequency. It turns out, for this case, tau sub p is not a function of omega. It's constant with respect to omega. And so this filter delays any frequency by one sample. It kind of makes sense. If you think this is the impulse response, right? What happens when you put an impulse in? Well, it's no longer an impulse, because the impulse is composed of a lot of different sinusoids, and they all they have their gains modified by different amounts. But you can sort of see that to the extent that it's a distorted impulse, it's rather than being centered on 0, it's now centered on 1. So the whole thing's been delayed by 1. And in fact, it remains symmetric, which is to say that all frequencies get the same delay. If I just go back to the actual look of this input-output here, it's kind of hard to see, but maybe you can see that this red line is a little bit delayed relative to the underlying slow variation in the blue line. It's one sample delayed relative to that. That's what the effect was. Okay, so that's phase delay. That's kind of the natural and straightforward one. The other kind of delay is this thing called group delay, and that is about not so much the delay of the kind of fine structure sinusoid, but the delay of the envelope of a modulated carrier, because it turns out that that can be something separate and something interesting. Yeah. 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 So when we're talking about phases, of course, we've always got this issue of pi ambiguity that we can get. You know, if I multiply a signal by -1, if it's a sinusoid, that's the same as delaying it by half a cycle. So when I'm talking about phase delay, you know, it's like, well, was it delayed by just one sample, or was it delayed by one sample plus a whole cycle? Because if the sign got flipped, that would be the appropriate way to understand it. You know, in general, you're going to have to look at the detail of the situation to decide which of those is more relevant. In this case, you know, this is obviously the natural way of understanding it. But if there were, I don't know, I can't give you a satisfying mathematical account for that. Typically, there's one interpretation which works out nicely, and there's one which gets messy because you have to have these arbitrary offsets. So yeah, if we included the phase, we'd have this. If we included a pi shift, then we'd have this delay, which was also, you know, which depended on frequency. So, yeah. Yeah. Okay, so the group delay. This is the kind of signal we're talking about. So this is a carrier, high-frequency signal that's been modulated, amplitude modulated by a low-frequency signal. We're just saying that x of n is some amplitude signal, which is the amplitude envelope shown in red here, times some carrier, cosine of omega sub c of n, which is the blue sinusoid we see here. And in this case, the carrier, a of n, is also a cosine, another sinusoid, but with a frequency omega sub m, the modulator frequency, which is much lower. So the carrier, the envelope is slowly varying compared to the carrier, which is rapidly varying. And we take this situation because it's a very easy one to analyze, because now we have x of n as the product of these two cosines. We can use this trig identity that the product of two cosines is the sum of two different cosines at the difference of the angles and the sum of the angles, or in this case the difference of the frequencies and the sum of the frequencies. Right, so in order to understand what happens to a signal when it goes to a linear system, we want it expressed as the sum of individual sinusoids, because then we just modify each of those sinusoids by the frequency response, by the magnitude and phase response of those frequencies, and we know what the output is. This thing is expressed as the product of two sinusoids. We don't actually know how to deal with that until we rewrite it as the sum of two simple sinusoids, and then we can say, okay, I know what's going to happen to this when I put it through the system. This is this kind of classic AM case where actually the spectrum of the product of these two sinusoids of different frequencies, even though if the amplitude were constant, it would just be a single frequency component omega c, what we actually get is two sidebands at omega c plus and minus omega m. So the modulator, the pure cosine modulator, splits that carrier frequency into two very closely spaced frequencies, just either side of the carrier. So now when we put them through the filter, each of these individual cosine terms is going to be modified by the frequency response of whatever system we're putting it through at those two different frequencies. So we're looking at we have these two different frequencies. We're modifying, because they're different frequencies, they're hitting different parts of the frequency response, although they're very close together. They're just omega c plus or minus omega m. Now, of course, we can build different h of omegas depending on what we want. And so let's assume that we've got a system here where the gain, the magnitude response is approximately flat in this range of frequencies. So both of these things are being carried through at about the same, at their original amplitudes. But maybe in order to get this magnitude response, we had to sort of sacrifice control over the phase response. And so we have the theta at these two different frequencies is slightly different. The theta for the lower part is theta L, and the theta for the upper frequency one is theta U. And in general, they're going to be different. So what happens to the signal going through this system? Well, we said that the output is just if the input is expressed in terms of a sum of sinusoids, the output is also a sum of sinusoids, but each with their magnitudes modified by the magnitude of the system response at that frequency, and the phase is shifted by the phase of the system response at that frequency. So we get these two terms in here again. The cosines are basically the same, but they've got these phase offsets, and the phase offsets are different for the two things. Now we can reapply our trig identity, and again we're converting now the sum of two cosines into the product of two cosines as the sum and difference of the two cosines that we're adding together. So we get back this carrier cosine of omega c n, with some phase shift, and this multiplied by this modulator cosine with some phase shift. And now these two phase shifts are different, and they depend on the two phases that we got at the two different frequencies that we had in the system response. Right? So we have a different phase shift for the carrier and the envelope, which is getting this point that we've actually got, if we interpret the phase shift as a time shift, we've got a particular time shift for the envelope, and it's not the same as the one that we will observe at the carrier. And that's what's called the group delay, the delay that's observed at the sort of the coarse scale on the modulator. So how can we characterize this better? Well, let's assume that the phase function theta is not constant, but is first order. So we're going to do a linear fit in the region of omega c. And so we're going to say, well, that's just what we're saying here, that in the region of omega c, theta of omega c plus some delta omega is the value at omega c plus some slope times the frequency, the difference from omega c. And so that's what's shown up there, this diagram, which is both small and hard to read and hard to reach, is kind of the critical thing here. The blue line is the actual true phase function, which is like one of these smooth curves that we saw coming out of these polynomial z's. The green line, the thick green line, is a local linear fit at the frequency omega c. So where omega c intersects, we have this center point, phi of omega c, and then we have this slope s, which is gives us a local first order approximation to the phases in that region. And so these two flanking lines are omega c minus omega m and omega c plus omega m, and then where they intersect, the phase curve gives us theta L and theta U, right? The two phase values we got for the two different components of the modulated signal. And so from the previous slide, we had that the carrier experiences a phase shift, which is the average of theta L and theta U, right? The sum of them divided by 2, which we can see under this linear approximation is just the phase of the center frequency. So that's kind of nice that the carrier experiences a phase shift, which even though there wasn't actually any energy at the carrier, it was only at these two side bands, it still appears to exhibit a phase shift, which is kind of what we expected, the phase of the frequency response at that frequency. And so that's the phase delay is what we see hitting the carrier. But the envelope, right, the phase shift from the previous slide here of the modulator is related to the difference between these two phase shifts for the two different components. So it's theta u minus theta L divided by 2, which from up here, because the difference between these two things is, each of these is omega m away from omega c. It's just omega m times s, the slope, d theta omega d omega. And so when we plug that in to get a delay, to become a delay, it's the negative of the phase shift divided by the frequency. And so in this case, it's just the negative of the slope, the derivative of the phase function with respect to frequency in the region of that frequency, right? And this is what we call the group delay. It's determined not by where that curve is, but it's what the slope of that curve is at the particular frequency that we're dealing with. And clearly, so we have this situation. So this is our original signal. It's got a carrier, the blue part, which can shift by some amount, and it's got an envelope, the red part, which can shift by some amount, which can be basically completely independent of the phase shift shown by the carrier. And each of those is determined by a different attribute of this phase function. So the black line is the overall phase function, theta of omega. The value of theta of omega at a particular frequency, or in particular, the ratio of that value to the actual frequency, which is kind of the slope of this straight line from the origin to the phase function, that's the phase delay, right? So that, for a given frequency, we're dividing by omega, so it's sort of, it's the arctan of those things at that angle, something like that. But the group delay, the phase shift shown by the envelope, it doesn't depend on where this is. It just depends on how rapidly this is changing, on the slope of this phase function at this frequency. And clearly, you can see that you can imagine building phase functions that vary those two things independently. So we can have different group delay and phase delay. To make this work, we made some assumptions, right? We assumed that the magnitude response was constant and unity, and we assumed that we were getting this nice first order fit to the, that we were approximating the phase function with a straight line. Typically, phase functions are relatively smooth, so if we have a narrow range of modulation frequencies, then this is going to hold. If not, then and this was like for one sinusoid, but of course we could have decomposed the envelope into multiple sinusoids, and it still would have worked, right? We could have said, well, this envelope, A of n, is composed of several different sinusoids. We sum them up. Each of them gets multiplied by cosine omega c. They each correspond to a couple of points on this, modulated spectrum, and they each experience some delay. If they all experience the same delay because the slope of the phase function is the same for each of those frequencies, then the entire envelope, even for some complex non-sinusoidal shape, the modification it shows is some delay, the group delay. If the phase function if the phase slope is not constant in this region, then they're going to start experiencing different delays, and the shape of the modulator is going to start getting messed up. That's what we call phase distortion, and one of the other things we might want to do with filters that we design is to try and fix this if this comes up. We've got a system with that kind of phase response. We could try and impose some extra phase modification on it to bring it back to linearity so that we can recover the envelope up to a delay. So the last thing I want to show you is just a quick MATLAB simulation. This is just a visualization. All I've done is plotted a curve of this kind, right? A cosine modulated carrier showing the fine structure and then the envelope. And then what I'm doing is first I'm going to shift I'm going to have a phase shift on the carrier without changing the envelope. Oh, sorry. Yeah. Now that was a phase shift on the envelope without changing the carrier, right? So you can see that the okay, and that's the other one. Let's run that again. So what I'm going to do now is you're going to see on the bottom curve the red line is moving, but the fine structure, the zero crossings of this blue line of the carrier stays fixed. So this is a group delay without a phase delay. You see how the blue curve sort of scales up and down, but the red curve is moving. But now I can do the converse, have a group delay which is fixed, and then change the phase delay. And we see that the red curve stays in the same place, but the blue line moves relative to it, right? And so that's sort of the difference between phase delay and group delay. If you've got a signal like this, an amplitude modulated signal, you kind of don't care what happens about the carrier. I mean, this is what AM radio is. You have some high frequency radio carrier, like 820 kilohertz or whatever, and you just modulate the amount of energy that you send down that thing. In the receiver, you have something which is tuned to that frequency, but then you just basically rectify it and low-pass filter it, and all you're left with is the envelope of the energy, right? And in that case, the system goes through the atmosphere. The atmosphere might have different gains at different frequencies, as long as including different phase shifts, as long as they're relatively constant within the bandwidth of the carrier, things are okay. If the phase or the amplitude changes too rapidly, even within the whatever it is, 10 kilohertz of modulation bandwidth you're putting on, then you get a distorted signal and you hear sort of bad, weird radio reception distortion. But in other cases, it may be that the envelope is not what you're getting at. You're interested in the fine structure, and then suddenly you care more about the phase delay. So those are the two things we distinguish. Okay. So I went through that relatively fast because I wanted to get through it. It's something that, almost most of the time we only talk about magnitude response, and we let the phase response be what it's going to be. Most of the time it's not too bad. But as you can see, sometimes it can be serious, and sometimes it can have serious impacts on what you're doing. So it's just something to bear in mind. Any questions? Yeah. I mean, all I'm doing, right, is I just calculated cosine omega m of n times cosine omega c of m, and I added different phase shifts to each one. But the idea is just so that you can visualize what the different phase shifts, that if we analyze this system which has a phase response, right, then we can characterize its behavior in terms of near frequency as a center point, what the actual phase shift of the carrier frequency is, which is going to give us the phase delay, the time offset of the blue lines. And then we can also characterize it as a slope, the first order fit of the phase response in that region, which is going to give us the group delay, which is going to give us the shift of the red curve. And those two things are separate. I didn't actually build those systems to do the simulation. I just wanted to give you something in your mind so you can see what the difference between those two things is. Right, well, you're always going to have some kind of linear fit around the carrier frequency, right? It's just that if the modulator, if the sidebands, carrier frequency plus or minus the modulator, move outside the linear region, then things get weird.